Jupiter is my one of my favorite planets, not my favorite. Saturn's probably my favorite. Um, it's the largest one. It's the fifth from the sun in its orbit. It starts right after the Kuiper Belt, right after all the terrestrial planets, the four. And I mean, it's crazy. Its mass is 2.5 times more than that of all the other planets combined. So you take Neptune, Saturn, Uranus, Mars, Earth, Mercury, Venus, you combine them all, they won't even add up to Jupiter, not even close. Um, but it's like slightly less than 1,000th the mass of the sun, which is kind of crazy to think about. Um, which just means that you can add up all of the planets, right? Every single one of them, and they would still be just about like 1/1000th of the sun. Not even close to 2/1000ths, which I mean, just a tiny, tiny amount. Um, I think Jupiter's like the third brightest natural object in the Earth's night sky after the moon and Venus. So night sky, not like the sun or anything. Um, but still, that's kind of crazy for it to be so far away. I don't actually know the distance. Might have to look that up later. Um, but it's just so far away from our Earth, right? And I think it orbits at about 5.2 astronomical units from the sun, and we orbit 1. So I guess the average distance would be 4.2 when they're lined up, right, at their aphelions or perihelions, the semi-major axis, and it varies, but I guess the closest they get is 4.2 AU. So that's still quite a long distance. I mean, 1 AU is like 99 million. No, I think it's more than 99 million miles. Maybe? I don't actually know. No, I think it's like 98 million. Yeah. So that's just crazy. Or sorry, 98 million kilometers. Oh, anyways. Um, so yeah, it's kind of crazy that it could still be the third brightest natural object and still be that far away. But it makes sense because it's just huge. It has like 318 times the mass of the Earth, currently, and maybe a few million years ago, it was even larger. It had, I think it's decreased in radius by like 50%, since it fully formed back when the solar system was still pretty young, like a few tens of millions of years old, and now it's like 4.6 billion. So it's quite a small time. Um, Jupiter is made up of like 90% hydrogen by volume, and it's like 75% by mass because it like the 10% of helium by volume makes up like 25% of Jupiter's mass because it's slightly heavier than, well, not even slightly, it's like 2 times heavier than hydrogen. So that makes sense. Um, and Jupiter oddly is like contracting because it generates more heat than the planet itself. And the planet itself absorbs from the sun, right? So if you see through like Kelvin-Helmholtz mechanism, through the Kelvin-Helmholtz mechanism, whatever, um, it's it's like that's the mechanism that's working within its interior, causing it to contract, because it radiates more heat than it receives through solar radiation, through the photons that hit it. Because the photons that hit it, they produce heat, right? A sidewalk on Earth, it gets hot because the photons are hitting the sidewalk, getting absorbed. I think basically. So it's like shrinking by 1 millimeter, which is like 0.039 inches per year, which I mean it's still a lot. So like at the time of its formation, billions of years ago, let's say 4 billion years ago, Jupiter was much hotter and was like twice its current diameter, which is insane to think about because again, it's 318 times our Earth right now, and its diameter, I think its radius. We measure things in Jupiter masses and radiuses because it's just so big. Like the masses of extrasolar planets and brown dwarfs, right? Because Jupiter, it's basically like a failed brown dwarf, so it's almost a star, right? We could have had a binary system in our solar system had Jupiter been, I think it's about 60% or no, 40% more mass, um, because with that much more mass, the interior would be so compressed that the volume would decrease despite the increasing amount of matter. Um, so the pressure from outside would kind of collapse it inside, right, with the gravity pulling to the center. Um, and Jupiter, it has about as large a diameter of a planet, for its composition that any kind of planet could achieve, right? Above that kind of radius or above that diameter, being larger would probably mean that it's a star already, and below that it's just any other planet, right? It needs 75 times more mass, um, to fuse hydrogen and be able to become a star, though. Um, and its diameter is sufficient, to be like the one of the smallest red dwarfs. Like the smallest red dwarf is only slightly larger in radius than Saturn, and Jupiter is much bigger than Saturn. So, I mean, we could have had a binary system, which is, I think, one of the more common types of solar systems in our universe. Um, Kind of, it's at 5.2 astronomical units from the sun, which is about 778.5 gigamiles, I think it is. It's like GM, capital GM, which is gigamiles. Um, so yeah, there's like such a large and rapidly rotating object that it's actually more of an oblate spheroid, much more than any of the other planets. Um, its rotation rate is like one rotation per 10 hours, which is much faster than the Earth, right? We rotate about one rotation per 24 hours. So it has a slight but very noticeable bulge around the equator. Um, so you could see any kind of picture, and you could kind of measure the up and down and the side to side, and you would see that it's pretty obvious. Even from just looking at it, it looks a bit wonky. But our atmosphere is divided into a series of latitudinal bands with turbulence and storms along their boundaries, right? So if you see all those bands of colors are different latitudinal bands, right? And the colors are made by they're made by different compounds that are rising, they're upwelling, um, they're coming up from below the atmosphere or below the atmosphere that we're able to see, and they come up from there and they reach the top, and then the UV rays, they create orange and brown colors from contact with those compounds. So those are kinds of the bands we see. So you can kind of figure out that a lot of those bands are made up of different kinds of elements upwelling from, or different kinds of compounds upwelling from below. Um, so yeah, a lot of those storms and turbulence are made along there. There's a lot of different circulation patterns, so every band kind of goes the opposite way from the one up and like above it and below it, which is why there's just so much turbulence, so many storms, right? A lot of anticyclonic and cyclonic storms around there, like the Great Red Spot, right? Which every Jupiter documentary has to mention. It's an anticyclonic storm made about like 22 degrees south from the equator, of Jupiter, and it was made through the contact between two of those bands, right? If you see below the spot, there's a band of white going along horizontally, and then right above there's a band of red going along horizontally. But the band of red, I don't believe, is what makes the actual storm look red. I think it's the accumulation of more and more gases within the storm that cause that. I'm not too sure which ones, but there's a reaction between compounds that cause it to look somewhat red as the storm grows. Um, so yeah, it's a very turbulent atmosphere. Uh, so Jupiter, right, along with its like 60 something, 70 something moons, um, 95 moons actually. Yeah, it has 95 known moons, which is crazy, right? We have one. But like two of the Galilean moons are literally just the size of the moon. Two of them are larger, right? And there's still a bunch of other moons that could all count for like 20 times more mass than the moon itself. It's pretty crazy. It has a lot of mass, like revolving around Jupiter. Um, so yeah, it a lot of people don't know this, but it actually has like a planetary ring system because of all of that mass located on Jupiter, right? It collects a lot of asteroids and a lot of dust and particles that are flying around Jupiter and around the Kuiper Belt, and it brings them in, drags them in. Jupiter is actually like supposed. It's supposed that Jupiter is kind of like the protector of the inner planetary ring, right, where the terrestrial planets are, because its gravity well absorbs so many asteroids coming at it. But at the same time, a lot of scientists believe that it does as much harm as it does good, because it also launches objects from the Kuiper Belt to our terrestrial planets like Earth. So it's like a net zero kind of situation. But it does absorb a lot of objects around Jupiter. It's around itself, right? Um, so yeah, it created like a planetary ring, like Saturn has a planetary ring rotating around it. Like definitely the one that most people know of is Saturn's, but Jupiter has a small one, right? And I think Neptune also has, or maybe it's Uranus. I don't know. One of the two. They also have a planetary ring around them that's very obvious. So Jupiter also has the largest contiguous structure in the solar system after the heliosphere, which is its own magnetosphere. Um, which it's very large. It's much larger than Earth's magnetosphere, and it also reaches all the way to the orbit of Saturn, which is pretty crazy because you measure the orbit, the distance from the sun to the Earth, right? And then the sun to Jupiter is 5 times that, and the sun to Saturn is like 9 times that, 9 times Earth's orbit radius. Um, so the magnetosphere of Jupiter almost encompasses the entirety of the sun to Jupiter orbit, right? It was made about a few million years after the accumulation of matter around the sun and the creation, the combustion of the sun, I guess you could say. Um, so it's believed to be the oldest planet in the solar system because of this, because it formed right after that. It's like current models of solar system origin suggest that Jupiter formed beyond or at the snow line, which is an area where it's a distance from the early sun where the temperature was sufficiently cold for volatiles such as water to be able to condense into solids, right? Um, so the planet began as a solid core, which then accumulated gaseous atmosphere. So currently, right, if you look at um, the makings of Jupiter, it has a solid metallic hydrogen core and an icy rocky core, an icy layer around that core. Um, so all of that gaseous atmosphere accumulated around that core. I think the core itself makes up for about 7 to 25 um, masses of Earth out of the 318 currently. So it's definitely very, very heavy. Um, but there's more in a gaseous atmosphere in terms of mass than the core. Um, so as a consequence of this kind of formation, the planet must have formed before the solar nebula was fully dispersed, right? Before it actually formed into all of the other planets and the belts, the asteroid belts we have around us, or otherwise accumulated into the sun. Um, so during its formation, Jupiter's mass gradually increased until it had about 20 times the mass of the Earth, which is approximately half of which was made up of silicates, ices, and other heavy element constituents, right? Things that are heavier than nitrogen, helium. We call a lot of like the metals, right? Oxygen, what is it? Carbon, things like that. They're not actual metals, but they're much heavier than the much more common, like tens of times more common elements like hydrogen, helium, which are the most abundant throughout the universe, right? Our world might be made of so much metal, right? And here I'm saying like things like oxygen, carbon, along with all the other metals, the heavy elements, right? Yet the actual universe is made up of mostly hydrogen and helium, which is kind of crazy to think about. There's just so much out there that is just those two elements. Um, so proto-Jupiter, it grew larger than 50 Earth masses and created a gap in the solar nebula, where it reached its final mass in 3 to 4 million years. Um, according to one hypothesis called the Grand Tack hypothesis, sorry, um, Jupiter began to form at a distance of about 3.5 AU, yeah, 3.5 AU, which is like 520 million kilometers from the sun. And as the planet created mass around it, right, interaction with the gas disk orbiting the sun and orbital resonances with Saturn caused it to migrate inward, right, according to this hypothesis, where it upset the orbit of several super Earths orbiting closer to the sun, which caused them to collide destructively, which later on supposedly made up the terrestrial planets that we have here, right? Um, so Saturn too began to migrate inwards much faster than Jupiter, according to this. And the two planets became captured in a mean motion resonance at approximately 1.5 AU from the sun, which changed the direction of the migration and caused them to go away from the sun instead and out of the inner system to their current locations, right? More than 5 AU away from the sun. So all this happened over a period of about 3 to 6 million years, with the final migration occurring about several 100,000 years later. Um, so the thing is, though, there's quite a few issues with this hypothesis, because the timescales of like the terrestrial planets forming, right? Because we've done a lot of scans on our own Earth, and like we've seen how long it took for it to develop and what its first age was, and it seems to be inconsistent with this hypothesis, right? Those elemental compositions, the measured elemental compositions, they seem to be um, much different than what the hypothesis is saying. So it's more likely that this didn't really happen, but rather that the initial formation occurred about 20 to 30 AU from the sun, and then it came inwards to its current location of 5 AU from the sun in approximately 700,000 years, during a time which was approximately 2 to 3 million years after the planet began to form. So Saturn, Uranus, and Neptune, they formed further out than Jupiter, and they would eventually migrate inwards, right? Uranus and Neptune would stay out a bit more, right? As we know now, they're much farther away than Saturn and Jupiter. So overall, this kind of formation case makes much more sense than the grand tack hypothesis. But honestly, the first hypothesis sounds much more appealing, much cooler. So I kind of wish that would have been the case, but it's not. Jupiter is one of two gas giants in our solar system, right? There's a separation between Neptune and Uranus, and that those two are ice giants, and Saturn and Jupiter are gas giants. They're made up of mostly gas and liquid rather than solid matter, right? So Jupiter is the largest planet in the solar system, and it has a diameter of about 140,000 kilometers, and that basically gives it a volume of about 1,300 times that of the Earth, which is insane. Its average density is 1.3 grams per centimeter cubed, though, which is much lower than those of the four planets in the inner part of the solar system, right? Earth, Jupiter, Earth, Mars, Mercury, Venus, right? By mass, Jupiter's atmosphere, like I said prior, is about 76% hydrogen and 24% helium. Because even though it's 10% helium by volume, helium is much heavier. Although it contains a lot of trace amounts of methane, water vapor, ammonia, silicon-based compounds, also some hydrocarbons and benzene, things like that, that we found out through infrared and ultraviolet measurements. So just about it's 71% hydrogen, 24% helium, and 5% other elements. That's the interior of Jupiter. It contains denser materials, so the amount of hydrogen is lowered as more of those heavier elements increase in percentage. So the atmospheric proportions of hydrogen and helium, right, the stuff we could see in the atmosphere of Jupiter, it's much closer to the theoretical composition of primordial solar nebula, which it makes sense, right? As we said that it was probably the oldest planet, so it developed first and was able to create a lot of that mass into itself. Neon in the upper atmosphere is about 20 parts per million, which is the 10th as abundant as in the sun. While helium is about 80% of the sun's helium composition. So there's definitely a variation between the sun and Jupiter in terms of what they're actually made of. But a lot of the same elements as in the sun can be found in Jupiter, right? Unlike a lot of other planets in terms of percent mass. So just talking about mass, right? Jupiter has a mass of about 320 times that of the Earth, 318 to be exact, and 2.5 times that of all the other planets, right? It's so massive, actually, that the very center of the sun, right, with the sun, lies at above the sun's surface at 1.068 solar radii from the sun's center, right? So Jupiter is so massive that it's altering its orbit with the sun, right? So it's more as if Jupiter and the sun are orbiting around each other rather than Jupiter is solely orbiting around the sun. That's just how massive it is, right? It's crazy how it can affect the sun in such a way. Instead of, because when you think about it, right, when there's a huge massive object, like when you think about the Earth and the sun, the Earth's orbit, the barycenter, is probably around the core of the sun. Because Earth is just so tiny that it doesn't actually have too much of an effect on the force, right? The gravity between the sun and the Earth. But Jupiter is just so massive that it has a very strong effect. 1.0 solar radii, right? Just about is 1.1 solar radii is a pretty big amount, right? The sun is huge, right? Earth's diameter is like 11 times smaller than Jupiter. Jupiter has a size of about a radius of about 1/10 the radius of the sun, right? So Jupiter is much, much larger than the Earth, and it does have a very real effect on its orbit, which is pretty crazy, right? Like I said before, Jupiter mass, right? MJ or M Jupiter. It's been used as a unit to describe masses of other objects, especially like extrasolar planets and brown dwarfs. Jupiter has kind of a weird internal structure. So there have been multiple scenarios on the formation of Jupiter right before we actually kind of found out with all of our missions to Jupiter and the studies and the spectroscopies and things like that. It was proposed right before the 21st century that one, the planet created first as a solid body, right, consisting of a dense core that had a surrounding layer of liquid metallic hydrogen and some helium that extended outward to about 80% of the radius of the planet, and an outer atmosphere of primarily molecular hydrogen. And two, that the planet collapsed directly from the protoplanetary disk, right, from the beginning of our solar system. It was a protoplanetary disk that was created as the gravity well around the location of our sun increased, and it accumulated matter from the dust and all that was surrounding it in the solar nebula, right? It condensed into a disk as the center started to spin around that disk, right? It created the plane on which the planets and all the objects in our solar system revolve around. That was kind of the disk that created all of that. So if it collapsed directly from that, it was expected to completely lack that core that's said in the first hypothesis, right? Consisting instead of just denser and denser fluids that were predominantly molecular metallic hydrogen all the way to the center. So not a solid core, but rather a core made of fluid. But, right, like I said before, data from the Juno mission show that Jupiter actually has a diffuse core that mixes into its mantle. So it has that metallic hydrogen core. It has the metallic hydrogen layer surrounding the rock and the ice core, and it extends to about 80% the radius of the planet. So it was kind of confirmed that the first process was most likely true. So this kind of process arose during formation, while the planet actually created the solids and the gases from the surrounding solar nebula. But it also could have been caused by an impact of a planet about 10 times the mass of the Earth a few million years after Jupiter's formation, right? So back to that hypothesis before, the formation period of about 4 million years, right? To travel all the way to its current position in the solar system, it was theorized that a few million years after that formation and a few million years after that occurred, there was actually a collision with a solid Earth, or with a solid planet that disrupted the originally solid core of Jupiter, right? So it's estimated that the core itself actually makes up 30 to 50% of the planet's radius, containing heavy elements, right? Like the one not ones that are heavier than hydrogen, helium. So that kind of combines to about, what is it, 1/20th, 1/30th of the entire well, like 1/20th, yeah, 1/20th of the entire mass of the of Jupiter, right? It's located within its core. Um, So outside of this layer of metallic hydrogen, there's a transparent interior of hydrogen, right? The pressure and temperature there are about at critical temperature, or critical pressure and critical temperature, where there's no there's no distinction between the liquid and gas phases at that critical point. It's in a supercritical fluid state, right? Supercritical fluids is like a substance where the temperature and pressure is above its critical point, and it's I think about below the pressure required to compress it into solid, so it's kind of in like a limbo between solid, liquid, gas. So this gas extends downward from the cloud layer, and it transitions to a liquid in deeper layers as the pressure increases, the temperature increases, right? It resembles something like an ocean of liquid hydrogen and other supercritical fluids, which is kind of cool to think about, right? There's a gaseous atmosphere, and then you have an ocean right below that. It's kind of a weird thing to think about. Um, so the gas, right, becomes hotter and denser as the depth increases, which changes into the supercritical fluids. And then later on, it becomes that rock and ice core. The atmosphere of Jupiter extends to a depth of about 3,000 kilometers below the cloud layers, right? And Jupiter's just full of cloud layers. It's covered with ammonia crystal clouds, right, which also probably contain ammonium hydrosulfide. Um, those clouds are located in like the tropopause layer of the atmosphere, right? A lot of the same atmospheric conditions that exist on Earth exist on a lot of other objects in our universe, right? It's not only unique to the Earth. So there are layers of atmosphere like the tropopause, the stratosphere, things like that. Um, so in the tropopause layer is the majority of clouds, right? They form at bands. They form in bands of different latitudes, which are all known as tropical regions, um, which are divided into light and dark belts, or light. I think it's lighter zones, and darker belts. So if you look at a picture of Jupiter, right, you would see that like the northern part of it, it's dark. It has dark bands, and then it goes downwards, and you find lighter bands, and then you go downwards again, and you find a darker band. So it's kind of separated like that. And these conflicting patterns, they cause a lot of turbulence, right? With some wind speeds reaching about 220 miles per hour, which is insane, right? These are really common in zonal jet streams around Jupiter. Um, which are basically like they exist on Earth as well. They're like fast flowing air currents in the atmosphere, where they're kind of located near the tropopause, right? The area where on Jupiter those are the majority of clouds. So they kind of just like start, stop, they split. It's jet streams, right? You hear about them sometimes in the news and things like that. Um, those zones in the atmosphere have been observed to vary in width from year to year. But the thing is, like, they've remained stable enough that scientists have named them. Um, Sadly, I don't know the names. But yeah, I think there's, what is it, 20 something different bands like that you could see with your eye from photos, right? Just, or at least from a good telescope. You could observe Jupiter itself from a good telescope. It's proposed that there's a layer of water clouds right below the ammonium right below the ammonia, which it's kind of cool, right? There might be water vapor on Jupiter. Um, and it's pretty crazy because if you look at Jupiter for long enough, you might observe electrical discharges, right? Lightning. It's been detected pretty often, and the bright flashes, I think they last. I mean, they last for a few milliseconds, but we've actually seen them. We've observed them, and so we believe that there's water vapor on Jupiter that is causing these electrical discharges, right? With those lightning blasts being about like 1,000 times more powerful than the ones on the Earth, which is crazy stuff. Um, so those water clouds are thought to generate those thunderstorms in the same way as Earth does, right? With heat rising from the interior, right? Storms like that are made when there's a hotter air area, right? There's hotter air below, and there's cold air above, and the air kind of the hot air kind of pushes upwards as the cold air comes downwards, and it creates a kind of vortex, I guess you could say. Um, Creating friction between the two areas, which causes lightning. I think it was first observed sometime in 1665, right? Which is pretty crazy. 400 years old. About. I believe it's 400 years old. It seems likely that it could be. Um, and I think so. It was possible to observe the Great Red Spot in 1665 because telescopes with an aperture of about 12 centimeters or larger are actually able to observe Jupiter in such detail to be able to see that spot. So it makes sense that someone living then with access to the equipment necessary to actually observe Jupiter in such detail would be able to see such a large storm, right? I think the storm itself is larger than Earth, which is pretty crazy because it's just a small, not it's like a pretty big dot on Jupiter, but it's definitely not as big as the entire planet itself, right? It might be like a 20th of the surface that we can see when we look at Jupiter, maybe a 30th. The Great Red Spot is a storm, an anticyclonic storm that rotates clockwise, and it's located about 22 degrees south of the equator, as I said previously. Um, and we've seen through the Hubble Space Telescope images of other red spots, right, quotation marks, near the Great Red Spot. So there's definitely a lot of other storms that exist on Jupiter, but this is just the largest one. And we've kind of theorized that these storms can actually accumulate and create red spots, right? Like the Great Red Spot, which is kind of how this one was created. It's theorized that happened. Um, so basically, the object that rotates counterclockwise with a period of about 6 days. Um, the maximum altitude of the storm is like 8 kilometers above the surrounding cloud tops, and I think its length and its width are about currently because it's been seen to decrease in size actually. It's pretty stable and it seems to be a permanent feature of the planet according to several mathematical models that have been produced. Um, but it's significantly decreased in size since we first found it in the late 1800s, right? Initial observations that actually calculated the size of the Great Red Spot said it was about 41,000 kilometers across. But by the time 100 years later, when the Voyager flybys occurred, it was found to have decreased by half to 23,000 kilometers and a width of about 13,000 kilometers, right? So it's a very large decrease. And even now, it's about 16,500 kilometers by 10,000, by 11,000 kilometers. So it's decreasing at about a length of 930 kilometers per year, which is a very large amount because the Earth itself, I think, has a diameter of about 14,000 kilometers. So it's decreasing in size at 930 kilometers, right? A 14th of the entire diameter of the Earth every year. Other than the Great Red Spot, there's also a lot of other vortices that have been observed around Jupiter's poles, right? Some polar cyclone groups in the North Pole with I think one group containing 9 cyclones, a large one in the center, right? Not as large as the Great Red Spot, but pretty large, and 8 other ones around it. And then in the south, there's also a center vortex, but it's surrounded by 5 large storms and a single smaller one for about 7 storms. So these kinds of storms are pretty regular around Jupiter, it seems, created by turbulence in the atmosphere. And you could kind of compare it with like the hexagon at Saturn's North Pole, which is also a pretty amazing natural phenomenon. It's on Saturn, right? If you look at the North Pole, there's this giant hexagonal shape created by storms. It's a cloud pattern. It's about 78 degrees north of the equator. Um, I think the sides are like 14,500 kilometers, which is longer than the diameter of the Earth by like 2,000 kilometers. So sorry, yeah. The Earth is 12,000 kilometers. I think I said before it's about 14,000. It's 12,500 kilometers large, about. Um, so that it's a very large hexagon. And it's a pretty crazy thing. It's also seen that like if you zoom in there, it looks as though there's smaller hexagonal shapes making up the hexagon. It's a pretty weird thing.